inside the vacuum chamber. Then in the heat treatment industry, most of the times we see like the diaphragm pump, roots pump, screw pump, rotary vane pump, piston pump. Then these like the rotary vane pump, the piston pump, these are used for generating from atmosphere to the 100 millibar or the 10 millibar. Then when we talk of the high vacuum level, this is the thermomolecular pump and the diffusion pump which has been used. For the gas binding, still there is because of their process requirement. Vacuum heat treatment are now using this gas binding vacuum pump. So we will see like some of the application, like some how this roots pump work, how the piston pump work, what is the basic operating principle of the thermomolecular pump and the diffusion pump in the coming slides. So this is like a very small picture of a rotary vane pump which is used for generating a vacuum inside the furnace from atmosphere, like from 1000 millibar to 100 millibar. So like this is our vacuum chamber, and this is a vane pump. Vane, it is known as a vane pump because there are the two different vanes which has been attached to the rotary part. There is also a spring because this area of crossing, this area of the volume, this is also changing. I have this video also which is running on the top of it. Like I'll just try to analyze it, which is a self-estimating, and it will show like how these vane pumps are working. So like when the vane pumps are working, like this is connected to this. Okay, so this is connected to the vacuum chamber. These vanes are rotating and they are separating this a very small volume of the particle which are there in the chamber, and it is releasing from this gas exhaust. And this is like the further compression of this gas is done so that we develop a very good something pressure above the atmosphere so that the gases can be released outside. So this video is like very small video which is like showing how the molecules has been removed from the chamber with the help of a vane pump. And you can see these are the vanes which are like it is connected with the springs because of the different change in the volume also. This is like allowed to move a little bit. So I think this video is visible to everybody.
Yes, it is visible.
Yeah. Okay. So this is another root pump, which is the second stage of the pump. So what we have seen is the vane pump. They have taken the atmosphere level, vacuum level from atmosphere to the 100 millibar. So this is the second stage. If we go up to the -2 and the -3, so this is like which is known as the roots pump. So with the video, you can see like how the molecules has been removed at this vacuum level also. And nowadays these roots pump they are coming with this frequency drive, so you can you can increase the speed of these rotors also up to the 100 hertz. So it will just because what happens like when the furnace is very new, we are getting a very good vacuum level of -4 and the -5, but during after working some years because of the contamination, because of the atmosphere condition, will not get that much of the vacuum level. So these roots pumps are used for like something which is working at the 50 hertz. Now you can start that pump at the 70 or the 80 hertz also. So just to make your tech times same, the generating of the vacuum inside the furnace is the same. Then use this kind of the booster pump. So this is another set of the pumps which is known as the diffusion pump. So what we have seen is like the vane pump, it is taken at vacuum level from atmosphere to the 100 millibar. Roots is taken from -2 to -3 millibar. Diffusion pumps are used like these are the very general pumps which we see everywhere inside the furnace where the high vacuum is required. So these diffusion pumps are used from when we have to generate a vacuum level of the -4 and the -5 vacuum level, which is basically used for the brazing application, the nickel brazing, and for the different processes also. So when you see this diffusion pump, actually there is no motor connected to the diffusion pump. It works on a very simple principle, that is the Bernoulli theorem. Like when there is an increase in the speed, there is a pressure. You will find a pressure drop at that particular area. So how this works is like these are at the below of this diffusion pumps. There are the heaters. These are the oils, which is a very special oil for the diffusion pumps. Most of the times the silicon or the mineral oils. So this heater is used to generate the vapor of these oils. These oils are now migrating upwards, and they are going up to the these ejectors. These ejectors will generate a very high speed, that is like a supersonic speed. And because of the high speed, there is a like localized vacuum created at these areas, and whatever the particle there inside the furnace, they has been dragged and they has been pulled down at the bottom. And this is an exhaust of the diffusion pump, which is now connected to the roots pump and the booster pump. So it will not be like directly connected to the atmosphere. All these pumps will work in a series. Like this diffusion pump will be connected to the booster, and the booster will be connected to the vane pump. So this is another chart which shows like different vacuum pumps at the different vacuum levels. So when we talk of the rough vacuum, which is approximately from atmosphere to the 1 millibar, what we find in the vacuum heat treatment is the most of the time you will see this is a piston pump, which will work from atmosphere to approximately 100 millibars or the 10 millibar. Then there is another set of pumps. This is like the vane pumps, which will also the roots pump, which is also like working from atmosphere to the 10 to minus 2 and the minus 3. And what we have seen like the diffusion, these are their normal working range is from minus 3 millibar to the 10 to minus 7 millibar. So this is their normal. If you want to go higher than this diffusion pump, then we have to move to the turbomolecular pump, which will go from 10 to minus 3 to 10 to minus 10 and the minus 9. But when we have to use the turbomolecular pumps to generate a vacuum of the minus 7 and the minus 8, the other things also become very critical, like what is the vessel, what is the inside cleanness we get from the vessel, what is the material of this vessel is manufactured. So I'll just try to show also like why these things are becoming more and more critical when we are using the thermomolecular diffusion pump. So at the industry levels, most of the time, this is the till diffusion pumps we use. And if it's going up to the very critical application and the very high quality of the part is required, like in the nuclear or in the medical application, we see like the turbomolecular pumps has been used. So this is an approximate cost of like every equipment have their own cost because of the consumers, also because of the electricity they are consuming. So the first thing is like whenever we are running any equipment, like whenever we are in any pump, this is the mechanical pump and this is the booster pumps and the diffusion pump also. So the cost effectiveness is coming, the efficiency of them is very good when we are running them in a very in their normal operating range. Like for the diffusion pump, it can work up to, you can start the pump at the 1 millibar also, but you will not get such a cost effectiveness from it. So when we are running from minus 3 and the minus 6, we are getting a very cost effective consumption from the diffusion pump. So that's why like in the normal heat treatment furnace, you will not find like the diffusion pumps are getting started at the minus 2 or the minus 1 level. Mostly they are started at the minus 3 level also. Sometimes there is a question from the customer also, like why cannot I start the vacuum pump or this diffusion pump at the minus 2 level, because it will it gives an idea like if I can start at the minus 2 level, then my vacuum level I will achieve the minus 5 and the minus 6 at the earlier time. Yes, you will achieve, but there are the repercussions also, because you will be consuming the more oil and you will be like not operating the diffusion pumps at what they meant to be operated. So this is another slide, which is just like to correlate between what we have seen previously at the mean free path and the molecular density with the different vacuum level and the pump. So this is like the very basic pump set. When you said the mechanical and the blower, that means like the vacuum level what we are talking is tends to minus 2 and the minus 3 millibar. So and then the diffusion pump and the ion pump, that is also like we are talking the vacuum level, the minus 5 and the minus 6. So like from the atmosphere, you can use this mechanical and the blower pumps. And when you see this, the mean free path of the molecules at the atmosphere level, this is like 6.5 times to minus 6. And when we talk of the minus 5, the minus 6, this is approximately 500 meters. So these are the, just to give an representation of like what vacuum level and the what mean free path we will getting with the different vacuum set. So when we see this diffusion pump which is working up to the -5 and the -6 vacuum levels, and you see this the molecular density and the mean free path. Actually, there is the mean free path itself is like approximately half of what we are getting at the atmosphere level. So that means like there is a very less particle inside the vacuum chamber, and what diffusion pump is doing is removing only the molecules of the air and the other contamination which are there inside the pump. So there is no actual removal of the air from at the -5 and the -6. So let's say like now we have seen like what are the different vacuum pumps, what are used, at what level they are used, and what is the cost effectiveness. So let's try to visualize like when we start a vacuum pump down inside the furnace, like when we have to go from atmosphere to -5 and the -6. -6 is like most of this application of the nickel brazing, they are talking about the -5, the -6 level.
कपड़ा फेंके
So
एसी मेरे को चिप चिप कर रहा है
so when we start a pump down from atmosphere level inside a chamber, at the atmosphere level there is like the air will be removed, and after that like the vacuum level is dropping from 1000 millibar to 500 millibar and the 200 millibar, and approximately then it reaches the 10 millibar and the 1 millibar. So as the pressure is getting decreased, what we have seen from the initially from the basic laws of the gas, like the temperature will also decrease. So there is a water vapor condensation inside the vacuum chamber. Sometimes if there is a leakage inside the cell of the, you will find like there's a ice formation is also there because of the low temperature. Then there is like the fog developing because of the low temperature, and the gas is getting outflow from chamber to the vacuum pump, and the gas will also be like a turbulent flow. You will see the turbulent flow inside the vacuum chamber. And initially at the atmosphere level, at the 1000 millibar, it is only the air which is a major component. The particle contamination from the parts, contamination from the vessel, and contamination from the inside hot zone is not so much. They are like there is a contamination, but that is not playing such an important role. But when we go at a lower vacuum, now initially the air has been removed, everything, now this all the contamination, they start playing a very good role in developing the vacuum level. Then from when we go from 1 millibar to the -4 millibar, now there is a very less gas density inside the furnace. And when we go by the basic or like ideal gas flow, this is the PV equals to nRT. So now there is only the number of the molecules which will developing very less molecules which will like, so the gas electrical and this thermal conductance will also change from the atmosphere to these levels. When we go from -4 to -6 vacuum level, which is like the application of the thermomolecular pump. So at that level, there is no air. This is only the molecule which is colliding with the vessel walls, and so this is like the at the molecular level what we are talking at the -7, the -6. So this is like in the every slide, in the every talk, what I am highlighting is like what I want to say is like whenever we ask a customer like just you are generating a vacuum, but the cleanness of the part and the cleanness of the furnace is also equally important when we talk of the -5, the -6. Because so this is just to represent that thing only, like when we are dealing with the furnace at the -4 and the -5 level in most of the brazing application or the different application of the heat treatment. At that level, there is no air inside the furnace. It is only the contamination which is coming with the parts, water vapor, some amount of the water vapor, and sometimes like during the operation also, in the production also, somebody is touching the hot zone, something is left inside the hot zone. These all things plays a very important role when we are generating a vacuum. It will not only increase the time, it will also hamper the vacuum pumps. So sometimes the oils also has to be changed very frequently. So this vacuum level just to give that picture, like at the lower the vacuum level, the more cleanness of the part is required, and the more cleanness of not only the part, the surrounding atmosphere is also equally important. Like in the area where in the southern part of Chennai or in the Maharashtra itself, when there is a rainy season, we like when we start to come down from the atmosphere, it sometimes takes a days to reach up to the -5 and the -6 level because of the contamination, because of the humidity and the vapors which are present inside the atmosphere. So this is another terms which is very popular inside this vacuum heat treatment industry. The first is the outgassing, the degassing, and the desorption. So when we talk of the outgassing, this is like the removal of the gas and the solids at the lower vacuum level. The degassing is like when we are giving a heat to a part, or when we are giving a heat to the insulations. So all the gas and the solids are getting removed. So this is like the deliberately we are giving a heat and we are removing these gas particles and other contaminants from the furnace. Outgassing is something like which is happening by itself. Desorption is also like from the surface of the solids and the liquid, and from the different materials, things are getting released. How these things are getting important and why these terms I have included is like we'll see in the coming slides. Like when we calculate the leak rate, all these things are become more important for calculating the leak rate, for understanding the what a leak rate is. This is also the another term, the vapor pressure of the material. So vapor, like everything has their own vapor pressure. So it is not like in the vacuum furnace we can heat treat every part and we can put anything, build of anything of any material inside the furnace. So what we see is like generally this zinc and the cadmium. You can see the zinc and the cadmium. They have a very low vapor pressure. Like at the -3 and the -2 itself, they start to evaporating inside the furnace. And if a part is made of the zinc or the cadmium, or there is a slightest of the zinc and the cadmium also, in the end product you will find like there is a depletion of the zinc and the cadmium. There is another application like which is the brazing application, the nickel chromium brazing. Like in the most of the stainless steels also you will find there is a good amount of chromium available. And with this chart, if you see like the 10⁻⁴ and the -5 millibar, the vapor pressure is, and the temperature at this below 1000 degree, you will find the vapor pressure is approximately -3 and the -4. And for the nickel application, the nickel brazing application, the vacuum level requires the -5 and -4. So we are working at a very at the same level where the chromium will start evaporating and start getting deposited on the furnace. So this is another picture. Like initially it was all the graphite insulation. These are the like black and the shiny. When you start putting the chromium parts and the stainless steel parts, sometimes you see like all the shields they have become a little bit of dusky, and it's like a mirror-like finish you are getting. So most of the time we feel like we are getting the parts in a good quality, but somehow this is getting not giving a good feeling. Like my furnace is getting discolored, or because of the gas is not good. But this is nothing but this is like the chromium deposition which happens to the most of the part. So this is like the something what we have seen as a theoretical part, like something getting evaporated, and this is the slide which is showing the practical aspect. Like yes, in practically also you'll see like the chromium deposition on the furnace itself. Then another terms, very important terms, what is the leak and the leak rate, which actually defines the health of the vacuum furnace, and it also defines like how good you are maintaining and what are the different parts which are there and how good quality we are getting from the vacuum furnaces. So when we see a leak is nothing but a hole or the permeability from a vessel cell. And what is the leak rate? Leak rate is the total of this. You can say the total of the leak which are there inside the furnace. It can be from the flap, it can be from the welding joints, it can be from the different things. So let us define the leak, because these are the very regular terms when we are operating a vacuum furnace. Sometimes we also ask to our customers like what is the leak rate you are getting from the furnace. So something to have a more knowledge on this. So these are the different type of the leaks. Like the first, which a furnace can have. So like outside is an atmosphere level, and the initially it is at -4 or the -5 level. So there's a one type of a leak can be the permeation, that is from the gas is leaking through the vessel cell itself, from the metal it is going through. Real leaks is something like when there is a leak or when there is a hole inside the metal part, or because of the welding there is a leak. Outgassing is something where the inside metal is getting outgassed. What we have seen in the previous slide, that because of the pressure inside, the vacuum level inside is so low, like the parts are getting vaporized at that level. Diffusion is also from outside to the inside. Backstreaming is from the vacuum pumps, like from the diffusion pump also. It is not like everything is going from vessel to the pumps. Sometimes because of that there is a change, because there is some difference, some minute difference between the closing of the valves and the closing of the application. And since vacuum levels are at a very vacuum pumps are at a very low vacuum level, there can also the migration of the particles from the vacuum pump to the vessel. Virtual leaks, something like with a blind hole, with the welding leaks, with the welding porosity. These are the virtual leaks. Interleaks is like all these vacuum funnels, they are connected to the different gases also. So internally also, like there can be a gas leak from a gas cylinder or from a gas chamber to the furnace also. So when we see this different, like the actual leaks, the internal leaks and the virtual leaks, from our understanding, and like what we will say is that these real leaks are like very easy to identify as compared to the this internal and the virtual leaks, and they are easy to identify and easy to block also. And basically these are from the seals, from the welding joints, from the base, from the brace joints, from the o-rings. These are like the real leaks. There are also the internal leaks which is like from the blind hole, which we cannot do, but this is like something most of the time has been missed. And so the killness of these virtual holes, so these are like little bit more difficult to identify. And the virtual leaks are like the outgassing of the part, which is like an standard phenomena which nobody can avoid. But all these things, what are they are doing is like they are since my vacuum level is at the -5, and if I leave this vacuum level at the -5 and I come after 24 hours, will I get the same vacuum level? No, we will not get the same vacuum level. The vacuum level is now changed from -5 to -4, or it can be the -5 also, but not at the same vacuum level. So what is happening, like all these gases and all these leaks, what they are trying, because the things are moving from the high pressure to the low pressure, so they are trying to reduce this vacuum level from -5 to the -4 or the -3. But we have to see like what all leaks will be like, which will be hampering our parts, like where the part quality will be the more critical, like for the
Mohinder, continue, please. What happened? Yes, Mohinder, you can restart now.
okay.
Just a minute. Now you.
Okay, so what we were discussing is like suppose there are the no other leaks, like there is no internal leaks and there is no virtual leak. So how, when and we are taking we have kept this vessel at a vacuum level, and when we are revisiting again, so how the graph will look like something like the number one, like there is all with the time the pressure will keep on increasing, because the outside pressure is approximately 1000 millibar and inside is the 10 to -4 or the -5, something lower than the atmosphere. And this phenomena will continue till we are reaching at the same vacuum level what is there at the outside. But because of this outgassing and because of the different leaks also, there is also a phenomena which we can see in the second number, like initially the pressure will keep on rising with the time, but after some time it's getting stabilized. This stabilization is because now what we have learned initially, because of the vapor pressure, now the vapor pressure, there is no the the pressure inside the chamber itself is good enough, like there will be no there is no evaporating of the metals and from the different material, so it has getting stabilized, so there is no outgassing and there is no, because the vapor, because the pressure inside the vacuum has reached. So combining one and two, you will see this is like the approximately graph which you will see when you are calculating a leak rate, like when you when you plot that pressure with respect to the time of a chamber when it is kept as a vacuum level. So you will find something which is going in this direction. It is also the same, like this is an very linear when there is no leaks from the out, there is no leak from the internal and from the outgassing also. But because of the outgassing, you will feel, so you will find like the things are getting stabilized after some time. So this is like how you calculate a leak rate for a fund for a vacuum furnace. It is very small thing, but it is like calculated to keep and to understand like our furnace is leak tight. There is no issues with the internal leaks and the external leaks, and it also helps us to maintain the good quality of the part after the heat treatment. So this is nothing but like we have kept the procedure is very simple. You have to pump down up to the maximum limit the vessel. Then you have to close the walls and you have to start reading, noting down the reading of the vacuum level. So suppose we are taking the reading for 60 minutes. So after the we have to first note the vacuum level at before the 60 minutes. Then after the 60 minutes, what is the volume of the chamber which we are talking, and this is the time which is the 60 minutes, and it is calculated in the mbar liter per second. This mbar liter per second is also like in the most of the European and from the different manufacturer from the region side. So like if we talk of the Europe, they calculate in the mbar liter per second the leak rate. But when we talk of the US customers, they don't take this volume into the consideration. They only talk of this millibar per second. So this is just a very basic formula for calculating the leak rates. So this is another slide which I'm trying to correlate a leak rate with the physical phenomena, like to understand like when we talk of the leak rate of the -3 and the -4 level. -4 is generally when everything is very clean and the furnace is very new. And generally like at the industry level, we'll see like the leak rate of the -2, everything is talking about. So when we correlate with the very physical formula, you can see like this is the equivalent flow. Like when we talk of the leak rate of 10 to the -1, it is approximately 1 cc per second. This is an equivalent flow. And in the bubble equivalent also, you'll see like there is a very steady stream which is flowing from something which is getting leaked. At the -2 level, it will be like the 1 cubic centimeter which is getting flowed at the 100 seconds. It is like, and at the if you see the bubble, it is approximately the 10 bubbles per second. And if we keep on going up to the -6 or the -7 level, this is like the 1 cc in the 2 weeks. And if we go up to the more lower than 10 to the -11, 10 to the -11 and 10 to the -12 is like where this all these helium leak detectors which are used uh, uh, for identify the leak inside the funnel. This is like the at this vacuum level they are working. The times -11 is something like 1 cc in the 3000 years, which is like if you talk of practical sense, this is like the very small leaks which we are talking. But in the industry, like the 10 to the -3 is a very standard leak rate which everybody asks for old furnaces also. And when the furnace is the new 10 to the -3, the leak rate which everybody is looking. You can correlate and you can get some physical appearance also, like the when you say of the -3, what is the leak level and how big is the leak itself. Since everything is like the leak is also nothing like the flow of the gases from inside to outside or from outside to inside. So at this level, you can see like this is also the viscous flow, which can be from the laminar and the turbulent flow. And when we are talking of the leak rate of the -8, -9, or the -11, these are nothing that the molecules which are flowing from outside to inside and from inside to outside. There is a one more term which is there is one more thing which most of the customer do that is a purging. Purging is nothing like you are putting nitrogen gas and then you are removing this nitrogen gas inside the furnace. So this is just a graph which shows like if we talk of like the 10 ppm of the oxygen inside the chamber of the 100 ppm of the oxygen, then how many times you have to do this nitrogen purging. Nitrogen purging is just filling the gas inside the furnace and then again removing the gas from the furnace. So it's like diluting the oxygen and we are removing the every time we are removing the oxygen content from the furnace or from the chamber. So when we talk of that approximately 10 ppm level of the oxygen, it is like 10 to the 15 times I have to do the purging. This is an like sometimes just to give an representation and just to reduce the oxygen content inside the funnel. Most of the time, these are the things which has been done. This purging, what we do is the purging is mostly when we have this the very large gas tanks installation, and like suppose we have a very high purity of the nitrogen which is has to be filled inside the gas tank. So and we don't want to like the gas tank itself there, so we'll do the purging, we'll remove all the oxygen which is there, we'll dilute the oxygen which is there, and we'll remove in the every purging cycle this oxygen content. This is just to get a better purity of the inside of a chamber. Then now we have seen like what are the different vacuum pumps, then what are the different vacuum level these pumps can go, then what is the leak rate also. Equally, it is also important, like since we have seen like the vane pump or the piston pump, they can go from atmosphere to 100 millibar, and then the second stage of the vacuum pump comes, that is a booster pump, which takes vacuum level from 10 millibar to the minus 2 millibar. And then the third stage of the vacuum level from the diffusion pump, which takes the vacuum level to minus 4 and the minus 1. So with the similar application, there is the same way the pressure measurement also follow the same route. Like there is no single gauge which will measure the vacuum level from atmosphere to the minus 5 and the minus 6. So depending on the what is the pressure which we want to detect, and what is the gas composition, and what is the accuracy and reliability we are looking. There are different vacuum gauges which will come in the picture, and which will which will play their role for measuring the vacuum levels at different stages. So when we talk of the vacuum measurement, these are the first is the direct method, like this which is not dependent on the gas, right? Like for the helium also, for the nitrogen also, for the argon also, we can use the same gas, and what this gauge is showing the reading, it is accurate. There is also indirect method, like which is on the gas dependent. So we'll first see the direct method. Direct method is like since we have seen like the pressure nothing like the force exerted by the gas molecule. So we are utilizing that force exerted by the gas molecules to measure the vacuum level. So these are the two types of gauge. One is this capacitive gauge, and one is this piezoresistive gauge. So capacitive gauge is like when you see this picture, this is nothing like because of the gas pressure from this side. These are the two capacitive plates which are there inside the gauge, and because of the gas pressure from the one side, we are getting a deflection of a plate, and because of the deflection of the plate, there is a different the capacitance level is getting changed, and we are measuring this capacitance level for correlating the vacuum level inside the funnel. So this is, so now what we have seen, we have measured the vacuum level or the pressure because of the force. It is not about like nitrogen or the argon. All the gases will exert the same force at this level. So this is like the gas independent system. Then the indirect method is like the gas dependent, where whenever the vacuum level goes very low, like 1 millibar and the 2 millibar. So at that level, there is not much force which the gas can exert to the vacuum gauge, like to this capacitance gauge or toward the diaphragm gauge. So what we are using is like the properties of the gas itself for measuring the different vacuum level. So this is like the pressure is nothing but this is like the number of the particle density. This is the Boltzmann constant, and this is the absolute temperature. So this is like the phenomena, and this is like the formula which will be used for the gas dependent gauges. We'll see the two of the gauges which is very frequently used in this vacuum heat treatment. First is this Prani or the thermal transfer vacuum gauge, which is like can measure the vacuum level from 10 millibar to approximately minus 2 and the minus 3 millibar. This is like the general range from this for this gauge. So how this gauge works is like we have a very fine white tube inside the gauge, and this is a wire which is connected to the electrical current. When we are passing the electrical current, there is a thermal conductivity which will transfer. Like there is a heat generated inside the wire, and there is a thermal conductivity which will happen between this wire and the gas molecule. But since the things are at a very low vacuum level, there is a very low gas molecules which are present. So you can see the pressure is directly correlated with the temperature in this case, and this is used for like the measuring this vacuum level from approximately from a 10 to minus 1 to 10 to minus 5 of this one. But since there is a thermal conductivity involved in this gas, there is also the heat dissipation and the heat losses. So it is not like there is also an accuracy level defined for these gauges, which you'll see in the different slide. So this is something like when we are using a Prani gauge, we have to make sure like what gas we are using for the which gas. Is this for the nitrogen, or it is for the argon, or it is for the helium? Because everything has a very different conductivity at that level. So this graph is just showing this is an actual pressure and this is an indicated pressure. So you can see like when we are talking up to the 1 millibar, everything is correlating. But when we go at above the 1 millibar like this is in the nitrogen and air, they are following this straight line. But this is not the same for the hydrogen and the helium, and similarly, it is not the same for the argon and the carbon dioxide. So we have to make sure like with the Prani gauge which we are using, we have to see like what is their correctness also. So this is because this is dependent on the gas. So most of the time these gauges are used from the 1 millibar to 10⁻³ and the -4, just to avoid any dilation. But if somebody has to use these gauges can be used for this for the nitrogen, argon, for the different gases also. But we have to put a correction factor inside these gauges, which every manufacturer can have their own correction factor, and which can be given, and we can try to get an accurate vacuum level. We try to correlate everything with the actual pressure and this indicated pressure. There is also another type of the gauge which is known as the cold cathode ionization gauge, which is very popularly known as the Penning gauge. The working principle is very simple. Like we have this anode inside the gauge, and it is surrounded by a cathode. So when a large electrical current is given, there is a electron movement from the cathode to the anode, and because of the movement of the electron from cathode to the anode, like these are the gas particles at these vacuum levels. So the -4 and the -5, actually what we are everything we are talking is of this particle density itself. So there are the very few gas molecules which are there. So while moving electrons from the cathode to the anode, they will have a collision with the gas molecules, and because of that there will be the spark emission, which is known as the spark current. And you will also see like there is a magnet which is connected to outside of this anode. This is just to increase the travel time of the electrons. Like because of the magnetic field, the electron will not directly go from the cathode to the anode. It will take a longer distance. It will just to make sure like the accuracy of the gauge is good enough, and it is colliding with the more number of the gas molecules while traveling from the cathode to the anode, and we are getting the better accuracy. So there are the many types of gauges also, but I'm talking only something which we see on a everyday on the vacuum funnel, like the Prani gauge and the Penning gauge are the very standard terms and very standard vacuum gauges which we found mounted on the vacuum funnel space. So this is like another with a different gauge, like the pressure gauge is there, then the diaphragm vacuum gauge, the complete range of the vacuum level, and depending on the different vacuum level, like from the rough to ultra high vacuum level, every gauge has their reliability and the correctness of the reading what they are giving. So this is just a chart for that number. So we can see like the capacitum diaphragm, which is used mostly for this LPC activities like low pressure carburizing, where the most of the gases is the nitrogen, helium, and acetylene are involved. And this gauge is not dependent on this the properties of the gas itself. It's working on the pressure which gas is exerting. So we can see like it can be used from atmosphere up to the -4 and the -3 millibar, which is a very good range. So you will find like at the most of the applications, the CDG is used. It is covering the complete range from the atmosphere to the -4, the -5. Then again, this is like the cold cathode what we are looking. This is the timing gauge. So when we see the operating vacuum level of this normal operating vacuum level, it is approximately from -3 to -7. This is the operation level of the panning gauge. So now what we have seen is like how vacuum is generated, what are the different phenomena which we see when a vacuum level is getting from atmosphere to the -5 and the -6. And similarly, like how the vacuum level will be measured from atmosphere to the -5 and the -6, what are the gauges used. And when we were discussing this, the -5, the -6 level, what we were discussing is the contamination of the parts. I just put it one slide also because this is also to give picture like whatever we are getting and whatever we are putting inside the furnace, this is not exactly the clean. So we see the like with the different processes and with the different application, there is a contamination on the parts itself. So what we see is like the first, there is a gross contamination, there is the oils and dirt which is coming from the atmosphere on the part. Then there is water and the chlorine also. This is the second layer, which is like just very fine layer. Then there is the oxide layer which is getting there. Then there is like the damage there because of the different operations on the machining we are getting. Then there is the finally these are the undamaged metal which will come on the parts. So what, whenever we are putting a parts inside the furnace, you have to make sure like we are removing at least this gross contamination and the subversion layer. These are the layers which has to be removed for from the part to get the better vacuum level and the healthy environment inside the furnace for getting the good quality of the parts. So this is also like most of the times we see like the furnace has been properly maintained, the vacuum level is completely maintained, that we are getting a very good leak rate. But whenever the part is coming inside, the part are not getting bright, the vacuum level is also sometimes not reaching up to the for the expected level. That can be because of the part contamination. This slide is showing that like the part contamination and the part cleanliness is equally important if we are looking for a healthy life on the vacuum furnace. This is a picture which shows like when we do heat treatment in the atmosphere and when we do heat treatment in the vacuum, what are the difference? Like with the look itself, we can say like the parts which are coming from the vacuum heat treatment, they are much cleaner. There will be the less post processes like the grinding and the cleaning of the parts will be like the less consumable. And if we go at the molecular level also, you will find like there is a change in the microstructure. Like there is a very good microstructure also, and you will not find the IGOs getting developing or the different things also at the molecular level. So it is not only at the surface level; it is at the molecular level. So we will find that the quality of the part is much better when they are heated heat treated from in a vacuum furnace. So these are the uh, different applications for a vacuum furnace. Like most of the time, the brazing, sintering, everything. I have highlighted some of the things in a red. This is to make sure like the first is the -5 and the -6 vacuum level, which is like an very upper limit of operating a vacuum furnace. So when we talk of the -5 and the -6, what I told is like the part cleanness, the inside of the cleanness of the furnace, the material what we have used for cleanness, the gauges, everything becomes very important because what we are working at a very extreme level of the vacuum levels. So another is when we talk of in terms of the temperature also, like the 1100 and the 1150. If we go to the different slides also, like for the stainless steel, for this nickel brazing also, which is most of the customers are doing in the vacuum furnace, and they are operating like at a very high temperature, which is like approximately 200 degrees centigrade and 11 degrees. And the vacuum level is also required for the -4 and the -5. So there are the two things like when we talk of a temperature of this 1000 to 1260 degrees. So there is no metal charge grid which can work up to the 1260 degrees. This is always like even if you are using a metal charge grid, it will not going to melt, but it will be distorted in such a way like you will not be again use you will not be going to use again in the same furnace. So at this level, like the not only this part cleanness, the charge grid which you are using, the fixture which you are using for placing the part, that is also become equally important because the temperature is like that. So most of the time the CFC fixtures has been used. Then there are different non-metallic non-metallic things are also which are developing. Like there is a new development where this CFC fixtures with the ceramic also has been used for at this high level. Similarly, for the -4 and the -5 vacuum level, the cleanness of the part, the inside of the cleanness of the furnace, that is also becoming really important for getting a very good quality of the part. So these are like the for the super alloy also everything is what we are discussing is at the very high temperature, 1260 and 30. This is just to make sure like we will not be using any metal charge grids or metal fixtures for placing our parts. It will be mostly the CFC fixture which we will be using. This is just, I think, most of the things are very well known to the people. So I'll just skip these slides for now. So these are the very good application of a vacuum heated furnace. This is like the low pressure carburizing with the high pressure gas quenching also. So I will not be taking much time on this slides because this is like something which has to be dealt with the process, and we have our separate team which, like, depending on the part, depending on the cycle, and depending on the quality required and the tolerances required, the different LPCs. But this is a like very good application of the vacuum heat treatment with the LPC. Like this is a new since it has been developed from a very long time. But nowadays, like, people are moving from the seal pinch furnace to the low pressure carburizing, and it can be either the gas pinch or from the oil pinch. So this is also like where it can be done only in the presence of a vacuum. Like you will have a vacuum furnace. This is like a, I'll just explain this cycle. Like you will create a vacuum level from atmosphere to the approximately 10 to minus 1 millibar. Then you will insert a gas. Gas will be like the nitrogen for start the convective heating inside the furnace. Convective heating is done to just equalize the temperature, and you are getting everything within the plus minus the 5. Then there is the ramp, and this is the carburizing temperature, which is approximately 960 or the 950, depending on the different the material has been used. And when we see this carburizing application, there is like the different boost cycle of the acetylene and the diffusion cycle of the nitrogen. This is like the alternate diffusion cycle of the acetylene. Depending on the like what is the cast depth which we are which is required on the part, these cycles can keep on varying. Why acetylene is used is like because at the low pressure, like at the 600 and the 500 millibar, these acetylene is like they are directly cracking on the parts, not on like in the atmosphere. So this is like where the vacuum level is very good application of the vacuum funnel. In the diffusion also, with the help of the nitrogen, we are all the carbon atoms, they are getting diffused inside the gears or different or in the part. Then we have the quenching cycle, which is done with in our case it is done with the help of the helium, which is running at the 20 bar, and this is like the quenching cycle for this part. So this is like application of the LPC and with the vacuum in a vacuum furnace. And second, there is a brazing application also, which is like a very good application of a vacuum furnace, where this like the everything is heated up to the preheat in the vacuum level. Then the preheat is maintained, and then the holding time of this holding time is just to melt this brazing paste or the whatever the brazing element which we are using. These are maintained and they have been solidified, and again the gas cooling or the gas quenching has been done at a very low pressure. So what I wanted to highlight in between this LPC and this brazing application is the part quality is very different when we see from a conventional furnaces. Like in the conventional furnace, you will find the soot formation is the more, or the maintenance is the more, and we are not getting the tight tolerances on the parts. But with the help of the LPC and with this high pressure gas quenching, we are able to maintain very good quality of the part. Similarly, in the brazing application also, like when the things has been done, like the vacuum brazing has been done, you will see the quality of the part is very different what we see in the conventional thing. Like because of the brazing application, there is like a very good brazing has been done, and there is like the capillary, because of the capillary reaction of this the brazing paste, everything is very intact, and there is no post process also, because the part itself is all the post process has been removed, and they're getting good part. So I will not be discussing more on this LPC and this brazing application. That we will like this is like the first lecture from our side, and it is basically on a very basics of the vacuum furnace. I just wanted to highlight like what are the different terms and what are the different laws which govern the vacuum furnace. So it may be boring for most of you, but in the subsequent lecture, maybe in a couple of weeks, when we will discuss more on the LPC and more on the brazing application of the furnace, like the different material and the different brazing application. And for the LPC also, like how the SQF and how the vacuum LPC are different, what is the part quality which we can get, and how to reduce the time, and what are the other things in other than the furnace which we require for the LPG, that we will be discussing in the coming lectures. So thank you, everybody. That's all from my side. If you have a questions, we can answer them.
Okay, thank you, Mahinder. Let me see if our chairman, Mr. Sudhakar, has joined us. Request all participants to put their questions in the chat so that they can be taken up one after the other. And Mr. Ramkumar, is there anything that you would like to add? Just a minute. Mr. Ramkumar, yeah. Is there anything that you would like to
Yeah.
add to the presentation?
I think the basics of vacuum, it has been well defined in the presentation, and as Mohindra mentioned, this presentation, today's presentation, just we have covered the basics. The future presentation will go in deep of LPVC, where we got a lot of questions from 2-3 members, and it has been already answered via chat. So further, I would like we will continue. I mean, if there is any questions, we can answer it
Yeah.
if you're able to.
Our
Apart from
chair,
that, there is no problem. Yeah.
thank you, Ram. Our chair, Mr.
Yeah.
Sudhakar Bonde,
Hello.
has joined us. He'll just take around a little bit of time to tell us a little bit about ASM International India chapter.
Hello.
Welcome, Mr. Sudhakar. We can hear you. We can hear you. Request you to give your comments.
Hello.
Hello. Yes. Hello. Hello. Sudhakar ji, I can hear you.
Hello.
Yes, you are
Vivek?
audible. Yes, you are audible. Please, over to you. Hello. Yeah. Please start. Up. Are you not connected to the audio? We can hear you.
Hello. Am I audible?
Yes, you are audible.
Okay. I am Sudhakar Bonde. I welcome you all and would like to brief you about our ASM International India chapter. We are based in Bombay. Our headquarters are in Cleveland, Ohio. And I earnestly request most of the members who are not our members to become our members and share their views with us, their knowledge with us, and with all the members. So that is my earnest request. And about our activities, you can refer to our website www.asm-india.com and be a part of the ASM movement. Thank you. Thank you very much.
Okay, thank you, our chair, Mr. Sudhakar Bonde. Now coming to the questions, Mohinder, the first question is by Mr. Santosh Thapar. He is asking, how much pressure is required for effective vacuum in carburizing? Is there any relationship between pressure and carburizing temperature in vacuum carburizing?
I think that is already answered, Dr. V. Like Ramkumar has already said,
Yes,
like for the vacuum.
you have already covered, but I would request you to repeat it again for the benefit of all the others.
Okay. So this vacuum carburizing, like usually it can be done from 1 to the 15 millibar, and the process like it is because of hello.
Yes, please continue.
Yeah. So mostly these vacuum carburizing, these are done at the 100, like 1 to the 15 millibar of the pressure, where this is the pulse of the acetylene has been given for this.
Okay. And the hydrogen is also put in at the same pressure?
No, hydrogen mostly this is not involved in the during the application of the carburizing, but these are for the activation which is done for the some of the application for activating the surfaces. Hydrogen is also used. But
how
depending on
would
the
you
like
compare vacuum carburizing with normal gas carburizing? What would be the quality aspects in the part that we would see different?
Like when you compare this from the atmosphere and when you go with the low pressure carburizing, the first is like because of the higher temperature at the low pressure carburizing, we can achieve a better gas depth, and because of the LPC also, and because of the quenching which is involved, the high pressure gas quenching, the tolerances level are also maintained at a high level as compared to the conventional carburizing.
Okay, so
So
the
like
case
if,
depth would be better. Would the
yes,
distortion be in better control, or that would remain the same?
no, distortion will also, you will find, if I'll say approximately, you will find approximately a very good tolerance levels are maintained. Like suppose if you are maintaining 40 to 50 microns in your normal carburizing, then it is also, there are customers who are maintaining the same tolerances with what they are doing in the SPF now at the 5 microns, the 10 microns also. So depending like where we are talking of the tolerance level, it is maintained. But yes, the tolerance level and the carburizing depth and the carburizing properties are better than what you see in the conventional method. Secondly, also like the decarburization and the IGO formation is also very less when we compare to the conventional method to the LPC method.
Normally, Mohinder, people talk about in terms of what is the what molecules have got left behind in the vacuum chamber that affects the quality of the vacuum. So, how do we know that the oxygen molecules or the water vapor molecules are not the ones which are left behind, and we have taken care of them in our process?
Like if you talk of the contamination level, like the first is like when you talk of the contamination which is coming from the gas side. So there is also like the dew point meter which is involved at the, which is mounted just at the entry point of this the vacuum level. So because of the dew point meter, you can maintain like how much water vapor and how much oxygen which is going with the process. And after the process, after the process, I think these are the residual gas analyzer which has also been involved for just analyzing like after the vacuum pressure, like what is the composition of the gas which we are getting.
So
But
that
mostly
means
what
if
we are
we are
talking,
looking at very fine vacuum heat treatment, the inlet dew points will also be of the order of -70 and above.
yes, they are approximately -70 and the -80 level.
Okay.
So
There
since
is
we
a
are
question from Mr. Nishant Shah of ASM Gujarat chapter. What is the vacuum pressure required for commercial heat treater?
vacuum level, like for commercial, it depends like what commercial heat treater is planning to do. Like if they are simply doing the hardening of the steels, then the -2 or the low vacuum level is also good. But since I said like there are the different application of the brazing application, if they are looking for a brazing application of the stainless steel or the nickel brazing, then the vacuum level will be approximately -4 to the -5 which is required. So depending on like what parts they want to heat treat and what application they are looking, it depends on very well. But most of the times, like if it's an hardening, then the low vacuum level is also very good, like the -2 and the -3.
This question again I am asking, is backup pressure verification as per CQI 9 possible in vacuum carburizing? Mr. Ramkumar has already answered this, but still again asking it again, that whether it is possible to do CQI 9.
Yeah, the CQ9 is possible. Like most of the customers, like who are using this LPC, the different customers, they are already CQ9 certified. But I am still not very sure about the back pressure atmosphere verification that I have to recheck.
Okay. The next question is again from Mr. Tapar. Is it possible to control austenitic grain size 5 or finer in vacuum carburizing, both in case and core?
That has to be like, I'll just check with my process persons and then I can decide. Like I'll just request Mr. S. Thapar to contact Ram Kumar, and if
Okay.
or Ram, can you take this question and just take the details from our process engine, then they can give it a more clear
Ram, you
answer.
are okay. I have now anybody can all participants can unmute themselves if they want. Okay, that facility is on now. Yeah. Just the next question. Are there any structural differences in conventional and vacuum carburizing?
Structural differences means if you're talking of the tolerance of a part itself, yes, there is a difference between the tolerance of the part which we get from the conventional and from the vacuum carburizing. And that is basically because in the vacuum carburizing, since the parts are finished either in the gas or in the oil transfer. So if we are looking for a very tight
Mostly it
tolerances
is
on the
gas
part,
nowadays. Though
if we
there
are
is
looking
some
for a
salt
very,
bath also, and other also is there, but mostly it is gas.
so if you are looking for a very tight tolerances on the part, then the LPC with the gas finishing is like an option.
Okay. Next question is, what is the normal market rate for vacuum heat treatment currently? Why is the cost of vacuum? What is the cost of a vacuum furnace in general?
I think that Ram Kumar can give a better answer because it's related to the cost. But
Yeah, we cannot say directly about the cost of the vacuum furnace, but I can say the running cost, it will be comparatively less compared to conventional heating. But it depends upon it again. It depends upon what type of process, what type of furnaces you're comparing. It depends upon everything. But if you compare about the running cost, yes, it is comparatively less compared to the conventional heating in terms of LPVC, because the ideal loss and maximum the consumables, everything is higher in the conventional heating compared to LPVC process, that is the vacuum process. It can be either gas quench or oil quench. It is cheaper.
and in general terms also, like if you're not talking of the LPG also, then if you see the complete cycle of a part, like it has been heat treated, now it is going for the grinding or for the different surface finishes also. So when you compare a furnace to furnace, yes, the vacuum furnace are the costly, their operating is also costly. But when you see the complete value chain of a part, you will find like the value, there is a reduction in the cost because of you have avoided so many of the processes after the vacuum heat treatment.
Mr.
In
Nishant
the
Shah
post
has some
processor,
comment to
yeah,
make. Please, Mr. Nishant Shah, please make your comment.
Yes, I want to know that can we do the alloy steel heat treatment, hardening and tempering in
Sir, your voice has gone down. Please tell again.
I want to know that can we do alloy steel like EN31 or EN19 in vacuum hardening for heat treatment, hardening and tempering? If yes, what is the quench pressure and what is the vacuum pressure required?
Like I said, for the hardening of the steel, so for the EN31 and the EN19, the hardening, yes, we can do the hardening, but tempering still we can do in the vacuum furnace, but tempering mostly people don't do because these are the low temperature applications generally, and for running of furnace, they avoid most of the time this tempering in the steam furnace because of the cycle. And the gas pressure is also
Yes.
approximately it will be the 9 to the 10 bar of the nitrogen which is required for the hardening of the steels.
And what about the pressure, quench pressure required in tool steel?
Tool steel is approximately 9 to 10 bar of the quench pressure of nitrogen.
No, I think tool steel in tool steel is required very less. As far as my knowledge is concerned, if I want to require tool steel hardening, the quench pressure require lesser than the alloy steel.
yes, comparatively lesser, but
Can you
yeah,
define that?
well, yeah, but right now we cannot define the exact quench pressure required. But we can get back to you on what is the exact pressure based on your geometry of your part, and we can define you what is the exact pressure is required for quenching.
See, we are a job worker, we are a commercial heat treaters. We never know what
Yes.
the job tomorrow is will come. And we have to
Okay.
standardize some.
Okay. So at
We
least
cannot
what is the yeah?
we
Yes,
cannot
continue.
we cannot put something today is working cannot give any job dimension today, but can we can ask for generalized idea.
Yeah, then Mr. Nishan sir, what I was telling is like the 9 to the 10 bar of the nitrogen pressure is the good enough, because when we are saying the 9 to the 10 bar is like the most of the steels are covered for the hardening in this. And the secondly, like when I'm saying the 9 to the 10 bar, that doesn't mean like you have to run the furnace always at the 9 to the 10 bar also. If your steels at
Yeah.
requiring like the 2 bar of the quenching, you can do at the 2 bar of the quenching also. So it can go up to the
Okay.
10 bar of the quenching. Like since you don't know like what is the part we are getting, then it is better to have like of the maximum capacity.
Okay. Thank you very much.
Any other questions from anyone or comment? Mohinder, I do
I
have
have one
comments in the
question.
chat.
Actually,
Yeah. Yes, Mr. Manral.
yeah, I have one question.
Yes, please go
For
ahead.
getting a part which is having case depth of around 1 millimeter, how much time it will take? What is the cycle time? I mean, from loading to unloading, how much time it will take in the vacuum carburizing compared to the conventional carburizing process?
Yeah, for this 0.9 or 1 mm case depth, for this again,
Yeah.
the time I can say is almost 50 to 60% of your convection heating. The time is comparatively less. Like you cannot say what is the time. It can be either 3.5 hours to 4 hours. It will be, but it will be less. But I cannot say exactly what is the time. But if you give me the composition, material composition, and everything, all details about your material, I can give the exact time to run the material to require the achieve the 1 mm case depth. But it is almost 50 to 60%
So
compared to
that
conventional.
itself is a good answer, that 50 to 60% less time compared to
Yeah, yeah.
conventional gas carburizing.
Yeah,
I mean,
yeah, yeah.
it is 40%
Absolutely.
less. It will take approx 50 to 60% of
Okay,
your
it will take
convention.
50 to 60% time, so 40% less.
Okay.
Yes. Yeah, if it is 1 hour, if it is 1 hour of a convention, it will take here, it will be 40 minutes, like that.
Okay.
And one more question I want to ask you, although you have answered it partly earlier. Apart from this microstructural benefit compared to the conventional this process, as far as the IGO and MMTP, all those things are concerned, and the distortion is concerned, and the surface is concerned, any other thing, any other benefit apart from these three things which I have spoken, any other benefit of vacuum carburized part compared to the conventional carburized part?
Like I said, like most of the time, this is like the two things, like at the molecular level at this. Hello. Like if
Yeah,
you
yeah,
talk
please
of the
continue. Yeah.
if you talk of the surface finish itself, like at the conventional level, because of the atmosphere, you will get the oxidized layer on the top, and because of that, you have to do the grinding or the other finishing process for the parts. But when you talk of the LPC, like mostly the quenching is done either in the oil or in the gas. So what you get the part is itself is clean, so it will reduce your the post process after the heat treatment processes also. And what we have said in the initial talk also, like you will get a better tolerances, better catch depth, and there is no formation of the IGO also. So these are like at the molecular level, at the metal level also, we are getting the better parts at every level. So it's both like the surface level
And how
also,
much?
and yeah.
Okay. Okay. And how much a furnace cost generally compared to the other? I mean, this vacuum furnace, how much it costs generally?
That depends on the like
I mean,
what
the
is the
normal
what is
capacity.
what yeah, that depends. Like we have a different sizes of the vacuum furnace, so depending on the part. Like we have this we give it a model as a 446 also, where the hot zone is approximately 400, 400, 600. So if you are looking at a very small part, then this is the smallest size which somebody can have. And when we talk of
No,
the
no. If I
LPC,
ask you, if I ask you, let's say furnace having capacity of 500 kg or the 1000 kg or something like this, can you give some
yeah,
idea about this? Let's say 500
that
kg.
yeah, that Ram can give an idea, but I think it will not be on this forum. That will like you can have a conversation on the mail for the cost and for the other details required for the installation of the furnaces.
Okay.
Yeah.
So
Okay.
thank you,
Okay.
Mohinder.
Thank
Thank you
you.
for an excellent talk. We had it was very interesting and very knowledgeable. We learned a lot of things about vacuum heat treatment, and we would definitely take you up on your offer for a detailed talk on vacuum low pressure carburizing, as well as a separate talk on vacuum brazing, because those are also very interesting topics, and very lot of new learnings are there for everybody there. Thank you all very much. And would
Thank you,
Mr.
everybody.
Sudhakar Bonde like to add anything? he is not there, he's already left. Okay, thank you everyone. Thank you for coming for the evening lecture. Thank you all. I will now be ending the lecture. Thank you so much.
Thank you.
Thank you everyone. Yeah, thank you.
Thank you. Thank you.
Okay.